Right now, you are moving at about 67,000 miles per hour. That's not an exaggeration. It's not a metaphor. It's a straightforward calculation of how fast the Earth travels as it orbits the Sun. At this very moment, without doing anything at all, you are being carried through space at a speed far greater than any airplane, faster than most bullets, faster than anything you have ever directly experienced. And yet you feel completely still. Pause for a moment and really notice that. You might be sitting in a chair. Maybe you're lying on a bed. Maybe you're standing somewhere quiet. Nothing in your body suggests extreme motion. There's no rush of air, no vibration, no sense of velocity pressing against your skin. If someone asked you whether you were moving, your immediate answer would probably be no. But physics says yes. The Earth completes one orbit around the Sun in about 365 days. The path of that orbit is enormous, hundreds of millions of miles around. When you divide that distance by the time it takes to travel it, the number that comes out is about 67,000 miles per hour. That means every single second, you move roughly 18 miles through space. In the time it takes you to read a sentence, you have already traveled farther than most cities are wide. And still, nothing in your senses reports this motion. This is where the puzzle begins. We tend to assume that motion should feel like something. If you ride a motorcycle fast enough, you feel the wind pushing against you. If a car suddenly accelerates, your body presses into the seat. If an elevator drops, your stomach reacts instantly. Motion in daily life seems obvious. But what those examples have in common is not speed, it's change. When a car accelerates, your speed is increasing. When an elevator drops, your velocity changes direction relative to the ground. When wind hits your face on a motorcycle, it's because you're moving relative to the air around you. In every case, your body detects differences in pressure, differences in acceleration, differences in forces. Now imagine removing all those differences. Imagine that everything around you, the air, the ground, your chair, your house, is moving at exactly the same speed and in exactly the same direction as you. There's no wind because the atmosphere is traveling with the Earth. There's no friction dragging you backward because you and the surface beneath you share the same motion. There's no sudden change in speed because Earth's orbit is smooth and continuous. In that situation, what signal would your body detect? There wouldn't be one. Your senses evolved to notice changes that matter for survival, sudden shifts, imbalance, impact, falling. They were never designed to measure steady, enormous cosmic velocities. From your brain's perspective, constant motion without change is indistinguishable from rest. So the mystery isn't that you're moving at 67,000 miles per hour. The mystery is that your definition of still has nothing to do with motion itself. It has everything to do with what changes and what doesn't in your immediate surroundings. That is the beginning of the illusion. Imagine you are inside a perfectly smooth airplane flying at 600 miles per hour. There are no windows. The engines are silent. There is no turbulence, no vibration, no shaking. The ride is so smooth that you cannot feel even the slightest bump. Now suppose someone blindfolds you. Could you tell whether the airplane is moving? Most people instinctively think they could. But think carefully. If the airplane is traveling in a straight line at a constant speed, there is no internal experiment you can perform to detect that motion. You could toss a ball straight up. It would fall straight back into your hand. You could walk down the aisles. Your steps would feel completely normal. You could pour water into a cup. It would flow straight downwards. Everything inside the airplane behaves exactly as it would if the plane were sitting motionless on the runway. This isn't just imagination. It's a fundamental principle of physics. The laws of motion inside a smoothly moving system are identical to the laws inside a stationary one, as long as the speed is constant. This idea was described clearly by Galileo Galilei in the 17th century. He imagined being inside a ship moving steadily across calm water. He pointed out that fish swimming in a bowl, flies flying in the cabin, and drops of water falling would behave exactly the same whether the ship was at rest or moving smoothly. Later, Isaac Newton built this idea into his laws of motion. And centuries after that, Albert Einstein realized that this principle wasn't just about ships or airplanes, it was about the structure of space and time themselves. The key insight is simple, but counterintuitive. Constant velocity is undetectable from within the system. You do not feel speed. You feel acceleration. If the airplane suddenly speeds up, you feel pushed back into your seat. If it slows down, you lurch forward. If it turns, your body leans sideways. Those sensations happen because your velocity is changing. Acceleration produces forces on your body, and forces are something your nervous system can detect. But steady motion, that produces no internal force. Now connect this to Earth's motion around the sun. The Earth is not jerking or vibrating as it orbits. It is not suddenly speeding up or slamming on cosmic brakes. It is moving in a smooth, continuous path through space. Everything on Earth, the oceans, the atmosphere, your body, shares that same motion. You are inside a very large, very smooth spaceship. And just like the airplane, there is no internal test you can perform to measure your constant velocity around the sun. The illusion of stillness is not a flaw in your senses. It is a direct consequence of one of the deepest truths in physics. Motion only becomes noticeable when something changes. Without acceleration, speed disappears from experience. Inside your head, buried deep within the bones of your skull, there is a small and remarkable system whose entire job is to tell you whether you are moving. It does not look impressive. It does not feel dramatic. Yet without it, you could not stand upright, walk straight, or keep your balance. This system is part of your inner ear. Within it are 3 tiny curved tubes arranged in different directions, each filled with fluid. These are called the semicircular canals. Nearby are small structures containing microscopic hair, like sensors embedded in a gelatinous material. Together, they form your vestibular system, your biological motion detector. But here's the crucial detail: this system does not measure speed. It measures change in speed. Imagine you are sitting in a car at a red light. The car is completely still. The fluid inside your semicircular canals is still too. Everything is calm. Now the driver presses the accelerator. For a brief moment, the car surges forward. But the fluid inside your canals lags behind due to inertia. It resists the change. That lag causes the fluid to push against the tiny hair cells. The hairs bend. Nerve signals fire. Your brain receives the message: we are accelerating. After a few seconds, however, something interesting happens. If the car continues at a steady speed, the fluid catches up. It moves along smoothly with the canal walls. The bending stops. The signal fades. You are still traveling fast, maybe 60 or 70 miles per hour, but your inner ear goes quiet. From your brain's perspective, you are no longer moving. The same thing happens in an airplane during takeoff. The initial push back into your seat feels intense. But once cruising speed is reached, the sensation disappears. The velocity remains high, but the acceleration is gone. Your motion detector has nothing left to report. Now scale this up to the Earth's orbit. The Earth moves around the sun in a smooth, nearly circular path. There is acceleration involved, because circular motion always requires a continuous inward pull. But that acceleration is extremely small compared to what you experience in daily life. It is gentle, steady, and consistent. Your vestibular system is tuned for sudden changes: falling, turning, stumbling. It evolved to keep you upright and alive on a planet's surface. It was never designed to detect subtle, cosmic scale accelerations. And more importantly, everything around you shares the same motion. The air, the buildings, the ground, your body, all are being carried together. There is no internal mismatch. If the Earth suddenly changed its orbital speed dramatically, you would absolutely feel it. The fluid in your inner ear would shift violently. But because the motion is stable and continuous, your system treats it as baselines. Your brain interprets stability not as zero motion, but as no change in motion. This distinction is small in wording, but enormous in meaning. You do not experience velocity itself. You experience deviations from it. That is why 67,000 miles per hour can feel identical to zero. Your body is not built to measure how fast you are moving through the universe. It is built to detect when something disrupts your balance. And as long as the universe carries you smoothly, your inner ear remains silent. Now let's look at something even deeper: the idea of a frame of reference. When we say you are moving at 67,000 miles per hour, we are quietly assuming something. We are measuring that speed relative to the sun. But what does relative to really mean? Motion only makes sense when you compare one thing to another. If you are sitting in a train moving at 100 miles per hour and another train moves beside you at the same speed in the same direction, the other train appears motionless from your perspective. A passenger inside that train could toss a ball straight up, and it would fall straight back down. From their frame of reference, they are at rest. But from someone standing on the ground watching both trains pass, both trains are clearly moving. So, who is correct? Both are. There is no absolute answer to the question, are you moving? Without specifying relative to what. This is one of the most unsettling ideas in physics. We tend to imagine space as a fixed stage, something solid and unmoving, while objects move across it. But physics does not support that picture. There is no universal, unmoving background. The Earth moves relative to the Sun. The Sun moves relative to the center of the Milky Way. The Milky Way moves relative to other galaxies. You can always choose a different reference point and get a different answer for speed. This means that when you say, I am sitting still, what you really mean is, I am not changing position relative to the Earth beneath me. You are at rest relative to your chair. Your chair is at rest relative to your house. Your house is at rest relative to the ground. All of you share the same motion through space. Because everything in your immediate environment moves together. There is no relative shift to detect. No wind sweeps past you at 67,000 miles per hour because the atmosphere moves with the Earth. No friction drags you backward because the ground beneath you shares your velocity. It's like being inside a giant spaceship where every object, every molecule, and every drop of air is synchronized. From inside that system, you appear stationary. This principle was deeply refined by Albert Einstein when he developed the theory of relativity. He realized that not only is motion relative, but the laws of physics themselves must be the same in all inertial frames, all frames moving at constant velocity. That means the universe does not privilege one viewpoint over another. There is no cosmic scoreboard keeping track of who is really moving. If you choose a frame of reference in which the Earth is stationary and the Sun orbits it, the mathematics can still work, though it becomes unnecessarily complicated. Physics does not forbid that description. It simply favors simpler ones. This challenges intuition because humans prefer absolute answers. We want to know the true state of things. Are we moving or not? Are we still or not? Physics responds with something subtler. Motion is a relationship, not a property. You are not moving through space in the way a car moves down a road. You are part of a coordinated system in which everything around you shares the same trajectory. Remove the comparisons and motion disappears. The illusion of stillness is not about speed. It is about shared reference. Now let's move from physics into perception itself. Your brain does not passively record reality like a camera. It actively constructs a model of the world using signals from your senses. And those signals have a very important feature in common. They are built to detect change. Consider your eyes. If you walk into a dark room and someone slowly increases the brightness over several minutes, you might barely notice the transition. Your visual system adapts. It adjusts sensitivity automatically. But if someone suddenly turns on a bright light, you instantly react. Your pupils contract. You blink. You feel the difference. Your retina is especially sensitive to contrast, edges, motion, differences between light and dark. If an image remains perfectly stable on your retina without any tiny eye movements, it begins to fade from awareness. This has been tested in laboratories. When a stabilized image is held perfectly still relative to the retina, it can gradually disappear from perception. Your visual system is not optimized to detect constant input. It is optimized to detect changes. The same is true for hearing. Your ears respond to variations in air pressure, vibrations. If air pressure were perfectly constant with no fluctuations, you would hear nothing. Silence is not the absence of air. It is the absence of change in air pressure. Touch works similarly. If you put on a watch, you feel it strongly at first. After a few minutes, you stop noticing it. The pressure is still there, but your nervous system filters it out because it is constant and predictable. Temperature behaves the same way. Step into a swimming pool and it feels cold. Stay in long enough and your perception adjusts. The water temperature hasn't changed much. Your nervous system has recalibrated. Your brain constantly subtracts the predictable background so it can highlight the unexpected. Now apply that principle to motion. If you suddenly accelerate, your inner ear and muscles detect it immediately. That change might indicate danger, falling, collision, imbalance. But if motion continues smoothly and consistently, your brain treats it as baseline. It becomes the new normal. From the perspective of your nervous system, constant velocity is just another background condition. This explains why 67,000 miles per hour feels like zero. There is no contrast signal, no deviation, no interruption. Your brain evolved in an environment where survival depended on noticing sudden threats, predators, obstacles, loss of balance. It did not need to detect planetary motion around a star. That information had no survival value. So natural selection never built a sensor for it. In fact, detecting absolute velocity would require something extraordinary, a reference to the entire universe. Your body would need access to a fixed cosmic backdrop to measure against. But physics tells us such a backdrop does not exist. So your brain does the only thing it can do. It monitors relative differences within your local environment. And when everything moves together smoothly, it labels that condition as still. What you call rest is not the absence of motion. It is the absence of unexpected change. And your entire experience of reality depends on that filtering process. Now let's examine something that seems like it should ruin the whole argument. The Earth does not move in a straight line at constant velocity. It moves in a circle around the sun. And circular motion always involves acceleration. Even if speed stays the same, the direction changes. And a change in direction is acceleration. So if acceleration is what your body detects, shouldn't you feel the Earth's orbital motion? At first glance, it seems like you should. In circular motion, there is always an inward pull toward the center of the circle. Physicists call this centripetal acceleration. Without it, an object would fly off in a straight line. The Earth is constantly being pulled inward toward the sun by gravity. That inward pull keeps it in orbit. So why don't you feel that inward acceleration? The answer lies in scale. The centripetal acceleration of Earth's orbit is extremely small compared to what your body normally experiences. It's about 0.6 meters per second squared. Now compare that to gravity at Earth's surface, which pulls you downward at about 9.8 meters per second squared. Gravity is more than 1,000 times stronger than the acceleration from Earth's orbit. Your body is dominated by gravity. It defines your sense of up and down. It presses you against the ground. It shapes your posture and balance. The orbital acceleration is tiny by comparison, almost drowned out completely. But there's something even more subtle happening. Gravity itself is not something you feel directly. What you actually feel is the support force from the ground pushing upward against you. If the ground suddenly disappeared and you began falling freely, you would feel weightless, even though gravity would still be acting on you. This insight became central to the work of Albert Einstein. He realized that locally, gravity and acceleration are indistinguishable. If you are inside a sealed box and you feel a downward force, you cannot tell whether you are standing on Earth or accelerating upward in deep space. This idea is known as the equivalence principle. Now consider Earth's orbit again. You, the ground beneath you, the oceans, the atmosphere, everything is falling together toward the sun. That is what orbit really is. Continuous free fall with sideways motion. Because everything is falling together, there is no internal distortion, no relative shift between you and your surroundings. There is no signal for your nervous system to detect. If Earth's orbital acceleration suddenly increased dramatically, you would notice. If it stopped entirely, the consequences would be catastrophic and unmistakable. But as long as it remains steady and small, and as long as every object around you shares it, your body has no reason to interpret it as motion. You are inside a freely falling system moving in a smooth curve through space. And just like constant velocity, smooth shared acceleration can become perceptually invisible. What feels like standing still on solid ground is, from a deeper perspective, continuous motion under gravity's influence. The Earth is not resting beneath you. It is falling around the sun. And you are falling with it, perfectly synchronized, perfectly unaware. Now let's think about the Earth spinning on its axis. Near the equator, the surface of the planet moves at roughly 1,000 miles per hour just from rotation. That's nearly 20 times faster than a commercial jet in flight. If you could somehow step off the ground without any reference points, it would feel like you were moving at incredible speed. Yet, once again, you feel nothing. There is no constant sideways wind rushing past your body. There is no continuous tug pulling you in a particular direction. The world feels stable, steady, and unshakable. The reason is simple but profound. Everything around you, the atmosphere, the buildings, the oceans, and the land rotates along with the Earth. The air does not resist your motion because it shares your speed. The oceans move in sync with the planet, And the ground beneath your feet is moving at the same rate as you are, because there is no relative motion between you and your immediate environment. Your senses do not detect the rotation. Motion is always perceived relative to something else. If everything moves together, nothing feels like it is moving. This principle applies not only to Earth's rotation, but also to the orbital motion around the sun. The chair you sit in, the house around you, the air you breathe, all share the same motion in space. There is no difference for your senses to detect, and therefore the high-speed movement becomes imperceptible. From your perspective, everything appears stationary because nothing is moving relative to you. The entire concept of stillness is, in fact, a description of relative motion. You feel still when everything around you moves with you in perfect synchronization. This creates a subtle but important illusion. You think you are at rest on a solid, unmoving planet. In reality, you are part of a massive system in motion. Earth rotates, Earth orbits the sun orbits the center of the Milky Way, and the galaxy itself drifts through the expanding universe. Every object in your immediate vicinity, the atmosphere, the trees, the oceans, your furniture, and even the atoms within your body, is moving in precise coordination with the Earth. The apparent stillness is not the absence of motion. It is the absence of detectable differences in motion within your local environment. Your body and brain are simply not wired to notice such smoothly shared movements. Even if you were to measure the speed with instruments, the sensations would remain unchanged. There would be no sudden force pressing against your body, no tug in any direction, no shifting balance to alert you that you are moving at incredible speeds. This is because acceleration, not constant velocity, is what generates sensory input. The spin of the Earth and its orbit around the sun are essentially smooth, continuous accelerations when measured relative to the local environment. The tiny accelerations involved are drowned out by gravity, which dominates your perception of up and down, and by the stability of your surroundings, which share the motion. Our nervous system evolved to detect sudden, significant changes in motion because those changes could signal danger, tripping, falling, or collisions. There was no evolutionary advantage in detecting steady motion at cosmic scales. Constant velocities and smooth orbital accelerations had no immediate consequences for survival, so the brain ignores them entirely. What you perceive as stillness is actually an agreement between your senses and the local environment. This means your sense of stability is a relative phenomenon. You are not truly at rest, but rather perfectly synchronized with everything around you, moving together as part of a vast, interconnected system in motion.